Hi girls, so tomorrow morning we're going to learn about loci or locuses, but loci is the right one, in the complex plane. I just want to show you a few different examples and get you thinking about how these work. So the first I'm going to show you is mod z equals 2. And so what we're tasked with doing is drawing a collection of points such that the modulus of z is 2. So if you remember what modulus means, it means distance from the origin. So I've got a point z such that its distance from the origin must always be 2. So I hope it's fairly clear that the locus is a circle, centre 0, 0, radius 2. Radius 2. I can also do this algebraically because that is the algebraic meaning of mod z, and that equals 2. And then I can square both sides and just say it's x squared plus y squared equals 4, which is a circle, centre of the origin, radius 2. So next I've got this one, which is very similar but different enough that we need to think about it carefully. So the way to think about this one is to actually rewrite the question like so. And then to think about this as a vector from this point to z. So I start with my, oops, I don't know what happened there, sorry. My point minus 2, and it's saying that the point z is distance 2 from this point. So hopefully it's fairly obvious that it is a circle, centre, so centre minus 2, 2, radius 2. And I can do the same thing algebraically, and I will show you how to do that algebraically tomorrow. Another one. So now we're on to arguments. The argument of this thing is pi on 4. Now again, the first step, I'm not labelling my axes just because it's kind of a pain in the bum with my setup to write small. So again, it's the argument from 3 plus I to z. So, that should be minus 3 plus I, shouldn't it? So if that's minus 3, 1, so then there's a dot there, and there's actually an open circle there, because the argument, so this is again a vector. If you draw a point z, and you take the vector from the point 3 minus 3 plus I to minus 3 plus I, then it is a null vector and it has no argument. So instead, I want the argument of this vector to be pi on 4, which means this angle here must be pi on 4, or 45 degrees. And it's just a straight line like that. Well, hopefully it's fairly clear that that point there is 4, and so it's the line y equals 3x plus 4. Sorry, x plus 4. Don't know where that 3 came from. Slope is tan 45, which is 1. And again, I'll go through that a bit slower tomorrow. I'd like you to think about why it is not this green section. Why does that part get excluded? And we'll talk about that tomorrow. Why it gets excluded. So lastly, maybe I'll do one more after this. So this says the distance from 2i, which is that point there, equals the distance from minus 1 plus I, which is that point there. Now we could do this algebraically fairly easily, but hopefully you remember that the distance, if the distance between 2 points is equal, then it's actually the perpendicular bisector, so it's this line here. I think it's going to do that, but I'll have to think about that a little bit. We'd have to do some algebra, but m equals minus 1 because this line here has m1. so it's perpendicular, and it goes through this point here, which is halfway up, so it should go through, oh no, it should actually go through there, I think, so I think it's actually y equals minus x plus 1. But tomorrow we'll think about that a bit more carefully and do the algebra to prove it. The last one I thought we might think about was this. What about if the it's the locus of z such that the real part of z equals 2, for example. Real part of z equals 2, just the vertical line. X equals 2 is the locus. Okay, so that's what we're doing tomorrow. And we'll obviously do a few more things on top of that, but not much more in fact. It doesn't get too much more challenging than this. And you'll see how to do it algebraically and visually, both of which work pretty well most of the time, but we'll learn which method is better given which information. Alright, I'll see you bright and early.